All right, let's start. Let me share the screen. Is the screen visible?
Yeah, it's visible.
Okay, okay, great. Okay, so this is the week number 4. And before we go any further, one important announcement regarding the exam. Someone asked what would be the format, if they will have coding questions or not. So the answer is yes, there will be 50 MCQs plus this is only for those who have registered for the exam. By the way, 5 coding question, coding problems, and they will have their own portal or platform, something where you can code and run the Python code. Okay, so that's it. And now let's begin with the recap. Okay, so this week was all about interpolation. And what's the idea? Idea is that no matter how strong, how big your computer is, at the end of the day, it's still going to record a discrete set of data points, right? So you have one data point here. So this is a function of time or x, and there is one independent variable and there is one dependent variable. So you have this data, then you are not going to have the data next to it, right? I mean, there are infinitely many points between any two discrete points. So you have data here, then here, then here, right? Uh, it depends how far they are on the whether how experiment was conducted, what was the sampling rate, etc. Right? This could be order of nanoseconds or something, or it could be higher also. But at any rate, it's not going to be continuous, right? In the most authentic sense of the word continuous. And maybe sometimes we need to integrate this or fit some curve, etc. So we need to know what is happening in between, and that is called interpolation. All right. So you can think of different schemes, right? So the very first scheme would be that you imagine that uh, between this range it's constant, then in this range it is another constant, then in this range it is another constant, right? This is how this is the first step in integrating, right? We assume that the function is constant within this delta x region. But this is a very bad interpolation. Can anyone guess why? Bad. It's because it's not even continuous, right? If we are getting some data from some physical experiment or something, we expect it to be continuous. So if it is not continuous, then we are not estimating it correctly. And we are never going to be able to estimate it exactly, right? If the function could be anything. But we want to be as close as possible. Right. So this is not continuous. So we should think of another scheme, which is the linear interpolation. So piecewise linear interpolation. This is how Python will plot the data, right? If we give the line plot, it says that okay, here the value is this, and here it is this, and there is a straight line in between, and then the function is this, then the function is this, right? So this is definitely better than the previous one, right? It's continuous. But now the issue is has kinks or corners, right? What do we mean by that? Mathematically, the slope or derivative for the first derivative is not continuous. Right? Let's take this point for example. In the left, the derivative is 0, right? F dash. Here, it's some positive. F dash x greater than 0. Let's say it's equal to 1. Right. So no matter how you zoom in, how much you zoom in, it's always going to be like this, right? So it's not continuous. So how do we solve that? We say that it's not actually a piecewise linear function, it's some polynomial, right? Or then we will see we could have splines also. But all this because we want to have our approximate function or estimated function to be smooth. You know what I mean? Not have corners or even cusps or anything. Alright. So before doing that, let's see how linear interpolation works. So we have 2 points, P1 and P2. Right? So we can imagine there is some x1 here and x2 here, and this is y1 and y2. Alright. And now we have an x that is between these two. So it's somewhere here. And we want to know how high it is. And we know that we want a straight line. So y should be somewhere here geometrically. So what we say is that uh, if y is higher than this, what happens? What happens is that this slope is greater than this slope. And if y is smaller, then this is smaller slope. This is higher slope. So we can calculate slope easily, right? So our target slope, which is the actual slope between P2 and P1, is y2 minus y1 divided by x2 minus x1. And the slope from y, let's say slope, estimated slope, will be y minus x1 divided by x minus x1. Or we can use x2 also, right? It will give the same result. And if we equate these two, that means we are doing linear interpolation. So this is one way to think about it. So let's do the math. So y minus x1 divided by x minus x1 is equal to y2 minus y1 upon x2 minus x1. Yeah. So we get y as y2 minus y1 upon x2 minus x1 times x minus x1 plus x1. Alright. So and you can rewrite it, you can distribute this term, etc. But this is one way to do, right? And so what this is? This is just a straight line. So this is m times x, and there is some extra term which is going to be your c. Okay, so you get a straight line and it has the same slope, and c is adjusted such that the line passes through both the points. And then you put in any value of x, you get the y, which will be a linear function of x. Okay. Another way, which is equivalent to this, is that we say that it's going to be a line that we know, right? Actually, that's the requirement. So that means that, and the requirement is that it should pass from x1, y1. So this should be satisfied, equation 1. And the other is mx2 plus c, right? Both should be satisfied. And when you solve this, you have two unknowns, m and c, and you have two equations. So you can get m is equal to something and c is equal to something, right? We know m is going to be this one, this value, and c is going to be this value. So you can solve it that way also. So all of these are equivalent. Huh? It's just that we should be aware of how to solve things. The third way, which is important because it is going to enable us to generalize to the higher order polynomial interpolation. Okay, and it is that we have one point x1 comma y1 and x2 comma y2, and somewhere in the middle we have x, and we want to know what is y as a function of x, right? And since it's linear, we can imagine that it is dividing this line into two parts, which has some ratio, right? So we can say this is t and this is 1 minus t. So t is the fraction of length of this line that has been covered by x, right? So as when t is 0, it's here. When t becomes half, it will be at the midpoint. At t is equal to 1, it is x2. So can we find out that ratio? Yeah. So it should be the same ratio on the x-axis also, right? So this is x, this is x1, and this is x2. So now we can write t as the distance between these two. So it is x minus x1 divided by total distance, which is x2 minus x1, right? And 1 minus t will be same thing, but x1 and x2 interchange, right? So x minus x2 divided by x1 minus x2, or you can write x2 minus x upon x2 minus x1. Okay, and now we can say that y should be a combination of y1 and y2, right? Because it's linear. So it is some combination of y1 and y2, and what these coefficients should be. So let's imagine if t is very small, then y1 should be very close to, y should be very close to y1, right? So if t is very small, then weightage is given to this x1 y1 point higher than this one. So these two are our weights, right? We are taking weighted average of y1 and y2. So the weight should be proportional to 1 minus t, and here it should be t. So now we can write this as x minus x2 divided by x1 minus x2 times y1 plus t is x minus x1 divided by x2 minus x1 y2. Alright, so I hope this is clear. By the way, I should have been slightly careful because in the lectures it is x0, x1, etc. Right? So I'm starting from 1, but you get the idea, right? So the coefficient of y1 is going to be x minus x2 divided by x1 minus x2. So this one corresponds to this one, and similarly this 2 corresponds to this 2. Alright, so all these three give the same answer, and they should. So is this clear? Okay. So in words, what this means is that if this is 40% and this is 60%, then y of x should be 60% of x1 plus 40% of x2, right? Because closer you are, higher the weightage is. Okay. And since we are not changing these values, the function is going to be a linear function. All right. Okay. So, and this enables us to get to the higher order polynomials, as they call it, Lagrangian. Okay. So if I have x0 and x1, it becomes y is equal to x minus something and x0 minus something times y0 plus again x minus something and x1 minus something y1, and this something should be other than 0. So it's going to be x1 and x1, and this will be x2 and x2. Okay, so what I have done is change x1 to x0 and x2 to x1. Okay, as in the lecture. So you get this formula. Now if we have multiple points, so now we have x0, x1 and x2, 3 points. So we know, right? So what happened earlier was, since we had only 2 points, there was a unique line passing through them, and that's something that we learned in our primary school. This is Euclid's hypothesis, right? One of the 5 axioms of Euclid. So if you have two curves, there is a unique line. Similarly, if you have 3 points, so unique line is basically x to the power 1, right? With some coefficient and constants. If you have 3 data points, there is a unique parabola passing through it, or a quadratic function. Okay, so now we can have a unique quadratic function that is passing through all these 3 points. Okay, and what is that function? So again, we have two ways to do it. First is, as I explained earlier, the second way in the linear interpolation part, that you say that our function is this ax square plus bx plus c, right? And then we put x is equal to x1. That gives us one equation, a x1 square plus b x1 plus c, and this is equal to y1. Okay, and similarly for x2, so again I made a mistake, we start from x0. Okay, so this is y0, and then for x1, and then for x2 is equal to y2. So what we have is uh, some combination of ABC, right? That gives us something, y0, y1 and y2, right? So this is going to be x0 square, x0 and 1, something like this. So we can invert this and get A, B and C. A, B and C, right? And that will solve our problem. So this is one way to do it, but the other way is the general way. And similarly, this you can do for cubic polynomial also, right? If you have 4 data points, you have 4 coefficient a, b, c, d, but then again you have 4 equations because you have 4 data points. So again you will be able to determine that uniquely. Okay, but the other way was to use the symmetry and use this same kind of equation, but there will be other terms here. Okay, so for linear, let me write again. It was x minus and x0 minus y0 plus x minus and x1 minus y1, and these terms were other than 0. So x1, and this will be x0, x0. Okay. So, and you call this the Lagrangian coefficient or multiplier something. Okay, so you said this is L0 of x, y0 plus L1 of x, y1. So now we have some coefficient and these are like your basis vectors. Okay, and now for degree n. So if you have n points, n plus 1 points, it means you have n degree polynomial. And if you have n points, it will be n minus 1 degree. Okay, for example, for 2 we got degree 1 polynomial. So it will be same thing again, L0 of x, y0 plus L1 of x, y1 all the way up to L n minus 1 x. Sorry, we have n points, so Ln of x, yn, and then each of this L, let's say L0, which was earlier this thing, right? X minus x1 divided by x0 minus x1. So now we have the same kind of term but with x2, x0 minus x2, and all the way up to xn. I use small. Okay. So x0 minus x, and this is going to be a degree n polynomial, right? So, oh, I used n plus 1 point c. So it will be degree n polynomial. Okay, and similarly, we can write for any general I. Li of x will be x minus something and then xi minus something. Now this something has to be say xj, and that j has to be different than I, and then we multiply all these terms. So product over j not equal to I, x minus xj divided by xi minus xj. Okay, and this is going to be degree of what polynomial? Number of data points minus 1. Okay, and so will be y, because it's y is just a linear combination of this L0, L1, etc. Okay, so this is the idea. You have Li, and then y of x is just sum over Li of x, y, I. Or if you are aware of Einstein convention, you can just write Lix, y, because we are this I is being repeated, so it is summed over. Okay, this is Einstein convention. If you are not familiar with it, don't worry, don't bother. And this sum will be from I is equal to 0 to n, all the data points. Okay, so is this clear? Any questions? You can unmute yourself and ask. Yeah,
Yeah, Harsh, I have a doubt regarding that function L0 of x.
yeah,
Yeah, in the lecture, Sir said that it's up to 2 points. I mean, like x minus x1 by x naught by x1 times x minus x2 by x naught minus x2 up to that point. I
right.
mean, he's not. Yeah,
No, that
so
was for t n is equal to 3. Sorry, n is equal to so total 3 points. If you have total 3
he,
points,
I think he wrote for general, like general time, I think. not for the like specific thing like n equals to 3 or
Uh, no, I don't really think so because then what happens for L2?
so. Okay, in that actually I will tell you the general equation.
Yeah,
Lj of x equals to pi.
yeah,
Before the j not equals to I, he will write like I comma uh, I
I,
not equals to j, x minus xi by uh, xj minus xi.
yeah,
That's the final
right,
equation. I mean,
right,
yeah.
right. So now compare this with this. Okay, it's same thing, but I will interchange J with I. So I'm calling this index as I, which he is calling J, and then
Okay.
I is being summed over. In my case, J is being summed over, right? So J is summed over. Get the point? This is same.
Get the point, but for L1 of x, he write like x minus x naught times x minus x2.
Yeah. So okay. So now J is equal to 1, right? So now it becomes
Yeah.
product of I not equal to 1 x minus xi upon xj, sorry, j is 1, so x1 minus xi. So now I can take value of 0, yes, because 0 is not equal to 1, so x1 minus x0. Now I cannot be 1, so it can be 2, so x minus x2 upon x1 minus x2. Now if you have only 0, 1 and 2, just 3 data points, it ends here. If you have third data point, so fourth data point, then you have other term x minus x3 divided by x1 minus x3. Okay, so this product is up to n, right?
Okay. But in the what I say, sir, in this video, he wrote
Hmm.
like up to these 2 points only. I mean, like x minus x naught by x1 minus x naught, x
Yeah,
min. I mean, yeah.
so
So
you are saying only this much.
yeah, yeah.
That will be true if you have just three data points. Okay,
Okay, okay. I got it.
yeah, okay. If you have third data point, you have this third term. If you have one more data point, you have one more term. Okay, that's my
Okay.
understanding. Still, I'll check once again, and maybe in the next lecture, if it is unresolved, then we can discuss it. Okay.
Okay, it's fine.
Yeah. So now that we have this formula for Li, we can see some things very easily. One is that what happens when x is one of the data points. Okay. So let's say x is equal to x3, and I want to compute y of x3. So it is going to be sum over Li of x3 times yi, right? By this formula. So we need to compute Li of x3. Now Li of x3 is product over all j not equal to 3 x minus xj divided by xi. So in this case xi is just xi because I is a free variable or free index minus xj. But x is x3. So I replace x by x3. Okay. And now what happens is that let's say for I not equal to 3, what will happen is uh, that j can take value of 3, right? And that will give our numerator as 0, which means Li of x3 will become 0. Okay. And if I is actually equal to 3, then our product becomes just x3 minus xj divided by x3 minus xj, which means this is going to be just 1 because numerator denominator are same in each and every term. So our Li of x3 becomes 1 if I is equal to 3, 0 if I not equal to 3. So now if we plug this into this, we get y of x3 is equal to, first is L0 of x3, y0 plus same for 1, right? L1 of x3, y1, L2 of x3, y2 plus L3 of x3, y3, and plus for 4, right? And all the way up to n. But we know that this is 0. Why? Because Li of x3 is 0 when I not equal to 3. This is 0, this is 0, this is 1 because when I is equal to 3, L3 of x3 is 1, and all the other terms will be 0, right? Because I not equal to 3. So what we get is just 1 times y3, which is y3, which means whatever our scheme is, it is at least interpolating because it is passing through x3 comma y3. Okay, because we saw that whatever the function was, its value at x3 turns out to be y3. Okay, and I chose 3 just arbitrary, right? It could be any random xj, and that means our Li of xj using the same analysis will be 1 if I is equal to j and 0 if I not equal to j. And the shorthand notation for writing this is Li of xj is just delta ij, right? Because definition of delta ij is 1 if I is equal to j, 0 otherwise. Okay, and now we can just write y of yj, y of xj, which is sum over Li xj times yj, and this is going to be delta ij yj. So, and what delta does with summation is that it only allows j is equal to I, right? So whenever j is equal to I, this term will survive. Otherwise, all the rest of the terms will get killed. So we just have y, I. Okay. So that's the proof. Oh wait, this should be yi, right? And this I is summed over, so I get y of j. So y of xj is equal to yj. So as I said, this 3 was arbitrary. Same will happen for x2, y2 also. And same will happen for x11, y11 also. So, and that is a requirement of interpolation, that it should pass through all the given data. Right? Whether it's a good requirement or bad requirement, that is subjective. But this is a requirement for interpolation. Okay. So the conclusion is that y of x passes through all data points. They are also called control points, by the way. Okay. So that is one thing. Another thing which professor discussed was error. And how was error defined? So if we have n points, then error is error is a function of x itself. So at every point you have a different error, which is the difference between fx, which is the real function, which we may or may not know, right? If it is coming from some experiment, it's a got particle data, so we don't really know. Okay, but whatever it is, minus our estimated function, right? And this is the definition of x. And the theorem states that there is some zeta which satisfies that this error is equal to fn of zeta divided by n factorial, and then the product over x minus xi. Okay.
Harsh, I have a doubt.
Yes.
Uh,
Yes, please proceed. Yeah. Who was that person? Okay, maybe he disconnected. Okay, then we'll proceed. If he rejoins, then we'll continue. I'm audible, right?
yeah, yeah. Hello. Now is
Ha.
it audible?
Yeah, it's audible.
Okay.
Huh.
So we know the only the points on the, or they say function, not the exact the how it evolves, right?
How it evolves as
I mean like,
in x or
uh,
time.
yeah, in the, uh, what they say, yeah, in y. I mean there is some points, right? Wait, I
Uh,
will.
let's say we know all these four data points. So
Yeah,
we
we know
we
only
just
the data point.
right.
Okay, okay. Go ahead, go ahead.
Hmm. Yeah. So and what is the argument? The theorem says that no matter what your function is, there is a zeta, there exists a zeta, and this zeta is going to be between x0 and xn or xn minus 1, whatever the range is. Okay, there is going to be a zeta such that this error is this much. So now you know some upper bound on error. Okay, so your function you can make it as funny as possible, something like this. Okay, it should be valued, but you get the idea, right? It could be anything, and you can evaluate the error function, or and maybe our approximate Tn of x is something like this, and the error is this gap, right? So let's say our x is this, and this is our error of x. So this cannot go to infinity. Okay, there is some upper bound on this one. It's because of the way that we have interpolated, and this upper bound is given by. So this is an exact value, but we don't know which zeta it is. So if we maximize over zeta, we get a upper bound for the error. All right, and again you can do the same thing. This is interesting. What if you write x as some x3? That's again x3. Then it is going to be fn. This means differentiation. Okay, so nth differential at some value zeta divided by n factorial, and then the product over all x minus xi. So since our x is x3, this x will be x3. But now this product contains 3, right? Which means there is going to be a term where I is equal to 3. which is just 0. X3 minus x3 is 0, which means En of x3 will be 0. Remember, this is a product. And what does this mean? By definition, that fx, the real function at x3, is the estimated function. So again, what is the conclusion? That y passes through x3, right? Because at x3, this gap between the real function and the estimated function becomes 0. Okay. And again, 3 is no special point. It's true for 4, 5, 11, 10,000. Okay. So we can write En of xj is equal to 0 for all j. Okay. Which means Pn of x passes through all data points. All right. And then professor gave one example. So let me just repeat it. And in case someone doesn't understand, please ask. Okay. And x was just two data points. So we were given just two data points. So now this energy, or rather the error function, becomes f2, right? We have two data points of zeta. We don't know what zeta is. Divided by 2 factorial. And now the product x minus 2 and x minus 5. And now we want to set an upper bound for this, because we are doing estimations, right? So we want to know how bad we can be, how worse our approximation or estimation can be. Okay. So f2 of zeta will be minus 1 over x square, that is the first derivative, and then the second derivative evaluated at zeta. So it becomes 2 divided by zeta cube. And now we want to know the maximum value of this. So uh, technically it's called supremum of zeta, and zeta has to be between 2 and 5 of 2 divided by zeta cube. Now we know how this the function looks like, right? As a function of zeta, it is a decreasing function for sure. So the maximum value you will get at the minimum possible value of zeta, which is 2. So this is 2 divided by 2 cube, which is 1 over 4. Similarly, this can also be maximized. So we can write supremum of x, and x is also going to be between 2 and 5. We are doing interpolation. Okay, x minus 2 and x minus 5. So this we know is a parabola, right? Between 2 and 5. Okay, and what we want to know is the maximum value of mod of this, right? We want to know how far we can be. So and we are in this region, and we know that parabola is symmetric about its zeros. So the maximum deviation, which will be negative in this case, so that's why we are taking mod, is going to be at the middle, which is 2 plus 5 divided by 3 by 2, so it's 3.5. Okay, so it's going to be 3.5 minus 2 and 3.5 minus 2, so 1.5 square, which is 2.25. By the way, you can just differentiate this and set it equal to 0, the standard traditional, that will give the same answer. So now our maximum error becomes product of this 1 over 4 into 2.25, and there was a factor of 1 by 2 or 1 by 2 factorial sitting here. Okay, and that turns out to be 0.28. So not bad. So what we know is that if we have 2 points, no matter what the function is, we can be off by at most 0.28. Okay, alright. This was 28125. So is this clear? Reason I did the same problem, and the reason I'm asking again is that it's very likely that you get a similar question in exam also, yeah, in NPTEL or in your own college course. Okay, so you should be ready to do these kind of small calculations. Alright, and then professor showed the code. We'll do the coding later, and you can do the same thing in 2D also, right? So in 2D you have a grid of points that is available, and let's say all these are available. And this is xi, so this is xi plus 1, etc., and here it is j, so yj and yj plus 1, etc., and we are interested in finding the value of the function at this particular point, okay, which is somewhere in between. So you can either go first horizontally or vertically. So and then you can do linear interpolate or even Lagrangian interpolate. So first you define these 2 points. What they will be? They will be xi comma y. So this is some x comma y general point. Okay, that is between I and I plus 1 in x direction and between j and j plus 1 in y direction. So first we get these points A and B. So A will be xi comma y and B will be xi plus 1 comma y, and we pretend that we know the value of these 2 points. Okay, even though we really don't. And if you are doing Lagrangian interpolation, then we pretend that we know all these values. In that case, what will be the p of x comma y? It will be same thing, right? Sum over I prime not equal to I used j earlier, same thing, and x minus xi prime divided by xi minus xi prime, and here we have p of xi comma y, but we don't know p is, let's call it p tilde, the function that we pretend we know. Okay, so we know xi comma y, xi plus 1 comma y, then xi plus 2 comma y, etc., but we don't really need to pretend to know this, because we can say that this point is between this point and this point, or if you are doing multiple polynomial, then between these all points. Okay, so now you can interpolate vertically. So p tilde of xi comma y will be given by, oh, there was a sum, right? Sum over all I. This will be given by sum over, let's use j, and product over j prime not equal to j, and now we are going in the y direction, so y minus yj prime, yj minus yj prime, right? And now p. or rather f, because we already know x, I, y, j. This we know, right? Because they are on grid point. So all in all, what happens is sum over ij, and because I and j are independent, all these terms are independent, right? So we can just write it like this: I prime not equal to I, j prime not equal to j, and then you have x minus xi prime, xi minus xi prime, and this term y minus yj prime, yj minus yj prime, and all these are coefficients of xi, yj. Okay, so this is a coefficient for I comma j, and then you sum over all I and j. Okay, so it's the same thing. If you have 3D, right, then you have another index k, another multiplication here, and then z minus zk, etc. Okay, so if you can do it in 1D, you can do it in any dimension. Alright, is it clear? Okay, then last thing which Professor briefly touched upon was splines, and we'll talk about splines in detail when we do the coding. But what's the need of spline? Because large number of data points means Lagrangian method or Lagrange interpolation, not good. We will see this. Okay. Why? Because you get lot of oscillations and you get a large amplitude oscillations also. Okay. So it's not bad. What happens is that there is essentially overfitting. So data is something like this. So it's probably something like this. Okay. But it gives something like this because we have large order polynomials. Okay. So in fact, this happens in machine learning also, neural network. Because what's a neural network? It's also kind of an approximating function, right? So rather than doing interpolation, it does, rather than estimation, it does approximation. So at the data points, it need not coincide exactly, unlike interpolation. Okay. But if it does so, there could be an overfit. And that's why you get very weird results sometimes on ChatGPT. I think nowadays you don't get so much, but earlier if you gave some math problem, you must have seen it just gives some weird thing that on its surface it looks very good, everything is good, but if you look at deep and see if the solution is correct, you will realize that it's just trash because it is doing this overfitting. Okay. So that's why we need splines. So what splines do is that rather than considering all the data points at the same time, it takes some data points and makes some curve, then take the next bunch of data points, take some curve, then the next bunch of data points and build some curve, and then impose some condition such that this slope should be same or the second derivative should be same, etc. Okay, so this is smooth, and wherever they are getting patched, it ensures that that is also smooth. So you get an overall smooth data, but it is approximated locally, right? Rather estimated locally, because this is controlled only by these 3 points or 4 points. It depends on what kind of spline you are using. So the most common one, which professor talked about, was cubic spline. And so the formula is given as this. So it's not the formula for f of x, but rather f double dash of x. Okay, second derivative, and that is a linear combination of xi, f of f double prime xi times something, and same for I plus 1. So this is when x belongs to xi to xi plus 1. Okay, and this is given by this coefficient is xi plus 1 minus x and xi plus 1 minus xi, and here it should be symmetric, right? So x minus xi and xi minus xi plus 1. Okay, and since we are writing this, so we are making sure that this is getting passed, right? So f double prime is continuous by definition, because if you put f I double prime of xi, you get f double prime of xi, the real one. Okay, so so this one we have to estimate this, by the way. But once you have this second derivative, you can find the second derivative at all the points, and by construction, this second derivative is going to be continuous. Okay, which means the first derivative and f, they also will be continuous. Okay, so this is the cubic spline, and okay, anything else in theory? Okay, any questions? If not, then let's look at coding part. Okay, so I've already done the coding because I realized otherwise it would take very long, and we anyways have an have a head start in coding, right? We spent 3 weeks, so I think you would be able to code on your own. And uh, this file will be shared with you, this notebook. Okay, so you can do it by yourself. So I'm first, as usual, importing NumPy and pyplot. Yeah, some students do this, write om or something, some religious symbol before writing the exam. This is our that thing. Although I don't believe in that one. But okay, and really IIT students also do that sometimes. So first we import these packages, and then we define a Lagrange interpolation function, that is a function of three things. One is x, which is an array of given points. Okay, all the data points, and y is the array corresponding to the y data points. And x interpolation is a number or a set of numbers where we want to interpolate. Okay, so it's going to be between the ranges of x, x min and x max, and we know the formula, right? Sum over li yi. So first we define first n to be length of x, number of data points, and we want to find the value of y, interpolated y, right? So we start from calling it 0, and then we start adding it. Okay, so for I in range n, so this is sum over I. Okay, and now we want to compute li. So li itself is a product of some terms, right? So we start calling the term yi, because at the end it's going to be a yi, right? So let me show you the formula. Yeah, this one. So we start by yi, then we multiply the first term, which is x minus x0 divided by xi minus x0. Okay, so it becomes this. Then again multiply the second term, x minus x0, x1 and xi minus x1. And we have to make sure that we don't multiply the term which is j is equal to I. Okay, so that's why we have this 2. If I not equal to j, this is how we write, right? I exclamation mark equal to, which means not equal to j. Then we multiply this term which we started by just y by this fraction. So this is x minus xj divided by xi minus yj, and this sum is over g. Okay, and after doing all the sum, we just add the term. So this becomes the sum over I li, okay, times ya. So after adding all the terms, we get the value of y. So that is the first function, which is the Lagrangian interpolation. And then second function is just piecewise linear interpolation, which we discussed. So, yeah, sorry about that. Which we discussed earlier, right? So piecewise linear interpolation looks. Do you do that? Yeah, this one. Okay. So you take consecutive pairs and make a straight line from that. And that is something that is inbuilt in NumPy. So np.interp will give you the function, and the arguments are going to be x interp, x and y. Okay. And then we want to see how it works. So we give an x some data points, which is 0, 1, 2, 3, 4, 5, and y is corresponding some random numbers that I have given 1, 3, 2, 4, 5, 9. So I have to make sure that both of them have the same length. Okay. And then x inter p is the set of points where we want to find the interpolated values, right? So I call it x dot mean. This is the minimum value of x. Okay. So because x may not be sorted array. So we start from minimum to maximum, and let's say we have 100 points in between where we want to interpolate. And the y interpolated value using Lagrange is just this function that we defined at x, y, and this values of x interpolated. Similarly, for piecewise, we have defined a function. Okay. And then we plot both of them. So first we plot x and y. These are the data points that are given. And this BO means blue and O means a dot. So you get a scatter plot with blue dots, and we labeled it data points. Similarly, for Lagrangian interpolation, we use a red dashed line. So it will be a red with lines. Okay. And this is Lagrange interpolation. And for piecewise linear interpolation, we use green and double dash. So it gives something like this. Okay. Dashed lines. And then we plot. So okay, let me run this. Yeah, so you get the result. So these blue dots are our original data that we got from experiments, and we want to know what happens in between. So green is what piecewise linear interpolation will do, right? Here to here, and here, and here. And it's bad because it's not smooth, right? There are corners everywhere. So we know that most likely in real life this does not happen. Physics is mostly continuous, and if it is discontinuous, it's at some points, right? It's not going to be discontinuous, or the first derivative cannot be discontinuous only at the data points. So this is a bad estimation. On the other hand, this Lagrangian gives a smooth kind of interpolation, right? So it's much better than this piecewise linear interpolation. For example, this one is just increasing, whereas the red curve knows that there is going to be another data point which is slightly smaller than this one. So it should start decreasing somewhere. That's why it is increasing higher. Okay. So, and what would be the order of this polynomial? Since we have 1, 2, 3, 4, 5, and 6 data points, we have fifth order polynomial. And at max fifth order, it could be fourth or third also. We'll see that in one of the assignments. Okay. So, any questions in this one? Is the code clear? It will be shared nonetheless, so you can play with it. So, by the way, there is a nice thing called Desmos. If you don't know about it, you should definitely check it. It looks something like this, and it is basically a graphical calculator for computer where you can make graphs and easily play around with variables and parameters and everything. So I did not make this. I found it online. Someone made this, but it's very interesting. You can change the number of data points that you want. So let's take 6, and then you get the Lagrange interpolation. Yeah, so it's nice. And good thing about this is that this is interactive. So you can change x1 and see how it grows and shrinks. You see, when I change x6, everywhere it is getting changed by a little bit. So if I change x6, look at this first maxima. It is also getting changed, right? And that's why it's non-local, because the change in x6 is influenced everywhere. Okay, and yeah, you can play around a lot. But let's do one thing. Let's increase the number of data points to 11. And what we see is that if you use common sense, then also you can see that it's nice here. It's quite smooth and everything. But something happens between x2 and x3. You get this large spikes that I was talking about. And that is something why we go beyond Lagrangian method, right? Because when you have large number of data points, now imagine we have 100 data points so that you have 99-degree polynomial. Then it's going to have this large fluctuations. And we definitely don't want it. Okay. So you can play around with this, huh? It's very fun, if nothing else. Okay, so in fact, we can see that in this one also. So this was the data points that we used, right? So let me comment this. You can add hashtag or you can press, select it and press control slash. Okay, and let's use this one. So it is same as above in the beginning, but then I have added more points. So in total, we have 11 data points. And now let's see how it generates. And again, you see this large spikes. You see here it's order of 5 to 10, and now you have 40 something. Okay. So that's why we go to splines. So before that, some interesting stuff that I found. The first one is called Brahmagupta's interpolation formula. I don't know why it's not working. I'll change the link. Yeah. But there is something called Brahmagupta's interpolation formula, which is a second order polynomial. And it was done in 7th century. So about 1300 years back. Okay. And before that, everyone used the linear interpolation. And he was the first one to do the second order thing according to this wiki page. I'm not an expert, but they have this shloka and the translation and everything. So if you are interested in it, just look it up. Interesting. Desmos thing we already saw. There are two YouTube videos. One is why is it not working? Oh, it's just giving me a notice. Yeah, this one.
longer and more complex.
Yeah, I won't play it. It's more than 1 hour, but it's just beautiful, amazing, mesmerizing. So she starts from very basics, and she talks about video gaming and everything, and how splines are useful, and it has lots of visualization because this subject is visual, right? At least for the beginners, it should be visual. So if you have 1 hour to spare, please check this out. It's just beautiful. Okay. It talks about splines and many other things also. Okay. And it's definitely not a part of course. Okay. So only if you are interested. And there is this other video which I wanted to actually show, just a part of it.
Hello, everyone. Days. Drafters used weights.
Yeah.
This
So
is
what it says is that people actually used splines physically to create this kind of curves for making ships and everything. So, and this string was actually called a spine, and it was made using such a material that it's slightly difficult to bend it. So, wherever there is weight, it will bend. Okay. And they wanted to make curves for ships, so they used this kind of weights.
actually how it was done in the old days. Draft
Okay. So, these are your data points. So, it's similar to what we did in Desmos, right? Just move the data points and you get an interpolation curve, which is just beautiful. Okay, so you can see this video also, and it is part of series. Okay, and one fun fact that Wright brothers, who made the first aircraft, right? They used these splines to shape the wings of their aircraft, which is something interesting. Okay, so yeah, so that is splines, and in fact, cubic spline is also there in SciPy, and the function is this inter p1d x comma y, and then you have to tell it that kind is cubic. So cubic is the one that was discussed in the class. Okay, so rest of them is the same. So let's just compare. Okay, so this is for 11 data points. So we know that this Lagrange was not giving very accurate measures in this part, right? Large oscillations. Now what happens with spline? It just goes away. So spline is this pink curve. Why? Because it is taking only the local effects into consideration. Okay, so it's much better than this one. It's local, but it's also smooth. See, so it's not like piecewise linear interpolation. So that's why people use splines. Okay, and there are other kinds of splines also. This is just one of the cubic one. All right, and the last thing is something that Agrim actually discussed, and this is his code. I should give him the credit. Agreem's call. Agreem is the person who takes Sunday tutorials. Okay. So in SymPy, you have a symbolic Python. So just like we do pen and paper, we think that computer can't do that, right? Because it has discrete data and everything. But you can give it the laws of calculus and everything, and it can actually do symbolic computation. And most popular example is Mathematica, right? In Mathematica, if you give integral of e to the power x from something to something 1 to 2, it will give the exact answer as e square minus e to the power 1 or whatever it turns out to be, right? Because it can do this symbolic manipulation and everything. And Python also has this called SymPy, and that library can evaluate symbols. Okay. So then you can define a Lagrangian polynomial for x value and y value, in which x will be treated as a symbol, and then you get a polynomial which will be function of this symbol x. but it's not just a symbol because it knows that it can take values, right? So you can substitute the values of x in the symbol of x. So let me just run this, and then let's say we have these four values. We are going to do this, okay, by hand also, and then it can do the interpolation, but more importantly, it can give this answer, symbolic answer also, the polynomial, and then you can evaluate this at any point. Okay, so this that is what he has done. So you define x as a lean space from 0 to 12, and y is the value of the polynomial with x substituted as x value for every x value in x, right? So this is one way to define an array, right? So for each value of x well in this array, we substitute the symbol x by that value, and then it will evaluate the function and it will plot it, okay, and it also prints this polynomial. So this is good because we can confirm our answers. We can check whether what we have done on using pen and paper is correct or not. Okay, and yeah, you can change the data points and see how it affects the polynomial, etc. All right. So let's go to the assignments. Any questions so far?
Yes,
Yeah,
one question.
please go ahead.
In that simple uh,
Hmm.
algorithm, the code that you have shown,
Yeah,
whether it also gives the error in uh, using that particular polynomial. Say,
it gives what? Can you repeat?
does it also give the uncertainty or the error in
Error.
the solution? Yes.
Error, it cannot give because we don't really know the function, right? We haven't specified what the function is which generated this data point,
Okay.
right? What it can do at max is what we did in the theory part, that maximize over all zeta and x, or for a given x, maximize for all zeta and see the maximum error. That can be done, yes.
Okay. Okay.
Okay,
I got it.
yeah.
Okay.
But if you want to know the exact error, you need to know the exact function.
Okay,
Okay.
we do in Excel, no?
Mhm.
Suppose we have experimental values and we use regression data or we use a regression line, right?
Yeah, yeah.
And there estimate how much is the variation in some of the measurement points.
Mm-hmm. Mm-hmm.
So,
Right.
uh, will that be help with that also? Will this also calculate
It is possible to do that in SciPy. One thing,
Okay.
SciPy can do error calculation. But the second conceptual thing is that interpolation is not regression. Okay. And what's the feature that demarcates these two or differentiates these two? In this one, we are required to pass the function through the data points. Okay. Whatever our estimated is, it should be passing through all the data points. On other hand, in regression, what we want is this total error to be minimized, right?
Right.
Yeah. So in this case, error is like proportional to f estimated of xi minus f real of xi square, and then you sum over all I, something like that.
Okay.
In this case, error is just a function of x. right? So there is no sum, first of all, and that error is just f of x real minus f of estimated at x. Okay. In fact, if
Okay,
you
okay,
calculate error at any xi point, which is what we calculate here, it will be just 0, right? Because at that point, we are required to pass it through the points. Okay. So these two are different things.
okay,
Okay. Yeah.
okay,
But SciPy can definitely do that. Okay.
okay.
Okay. Now let's look at assignment questions. And these are going to be slightly controversial, some of them. Let's see how it goes. So the first one is interpolation is the method of interrelating, estimating, integrating, and combining. So write your answer in the chat box using 1, 2, 3, 4. Okay. So first is interrelating, 2 is estimating, integrating, and combining. 2, 2, 2. Okay, Aparna, Dipankar, Rubhadra. Yes. So it is estimating. And why is it so? Maybe you can. Yeah, why is it so? Because uh, we have some data points and we want to find what is happening here, right? And we want to estimate it. We can be far from it, but we want our estimate to be as best as possible. Okay. And integrating will come later. Interpolation is not a method for integrating. It is used as the first step for integrating. Then we can apply the method of integration. But the interpolation in itself is just estimating what happens in between. Okay, so right. So the second option is the right one. Okay. Interpolation is done by curve fitting, regression analysis, curve fitting and regression analysis, or none of them. So three, three. Yeah, so three is the answer given by NPTEL also. So this is from previous question paper, right? So they say curve fitting and regression analysis. So this is answer key. But I personally would beg to differ because as we saw in the regression analysis, this constraint is not that the estimated line should pass through the given data points. Okay. So I think this is not there and therefore the correct answer should be curve fitting. This is what I think. Does anyone have a different opinion? One, Dipankar. Yeah, thank you for supporting me. Yeah. Okay, so let's proceed. Error is equal to, again, slightly vague. So we can only answer this in context of what is discussed in lecture, right? And in lecture, we have seen this error function was, where is it? Error function is given by this formula. And if we use this formula, this is just distance. By the way, I think there should be a mod here. Okay. But in any case, it's a distance between the data point and estimated value. Okay. So let's see. Distance between the data points, square of the distance, half the distance between data points, and none of the mentioned. So again, it's unclear what they mean by data points. Are those the given data points? Then none of them is correct, right? Because error itself is a function of x. But if they mean by given data point and estimated data point, then the first one should be the one. But I'm sure there would be some uh, contest contesting opinion. Yeah, so 2, 4, and 1. Yeah,
It can be MS, MS means like two option can be correct one. So second one also, it means the same one if you are finding out the distance.
second one. You mean the square of the distance?
Square also, and that half distance, but it's not like fully correct one. But in the error formula, we have a square, but we are taking RMS value like for the that thing.
No, no, we are not. We saw, right? In formula, it's just uh, what is error of x? It's just mod of f of x minus Pn of x. So where is RMS in this?
No, in not in this formula.
Yeah, yeah, you
In
are
the
right
general,
in general.
yeah.
Correct. In general, people do use RMS or in fact just MS, right? Uh, Especially in neural networks. Many people define this energy or cost function as half times sum over y minus y prime square, where one is real value and one is estimated value. Okay, in that case, it will be half the square of the distance between data points. You can ignore half because half just sits there because you want to minimize this, right? So you are going to differentiate it, and that will pull out this 2 outside. So you want it to be cancelled so that you get a nice linear equation. But even if it is not there, you want this quantity bit to be minimized, and then error would be square of the distance. Okay, and half the distance is same as saying full distance because you basically want to minimize it. So the factor should not matter. So yes, you are right. In general, it could be the second option, the closest one. Okay, but I think we should go by the definition of what is discussed. I mean, it is asking for definition, right? We can define error to be anything. It could be error is a door. That is also a valid definition. So what is defined in the lecture? That is the first. Does everyone agree with this?
Yes, yes.
Yeah. Okay. Fourth one, the last controversial one, hopefully, which produces smoother interpolants. Okay. So first is what is smooth and what is smoother. So this ER indicates that we want to compare between these two, right? Comparative degree. So if we compare between polynomial and spline, then by definition it can't be this one, right? Because you want to compare between this, unless you want to say that both of them are equally smooth. And the second question is, what do you mean by smooth itself? Okay, there are multiple interpretations, subjective interpretations. Mine is following, then you can tell yours. Okay, so people, Anil Kumar wrote 2, Srihari 2, Dipankar 2, okay, Virabhadra 3. That's it. So my interpretation is following. Smooth generally means that the derivative, first derivative, is continuous. This is what in maths they mean by smooth. Okay. So which produces smooth interpolants? Both of them produce smooth interpolants. Now which one of them is smoother? That that cannot be answered using this definition, right? Because it can be either smooth or non-smooth. So let's upgrade the definition of smooth. So smoothness is up to which order, as yeah, Veerbhadraji is saying. If we can call it n smooth, if it is smooth up to nth derivative. Okay. Now under that interpretation, which one would be smoother? In fact, one of these two has all the derivatives continuous. Is it the polynomial or spline? So that will be polynomial, right? Because polynomial can be differentiated infinitely many times. If you have x to the power 99, first we'll give x to the power 98, then 97, all the way up to x square, then x, then constant c or 1, then 0, then 0, then 0, right? So it can be differentiated infinitely many times. On the other end, spline is, well, it depends on what kind of spline you are using. But let's say it's cubic one, then up to second degree it's going to be smooth, right? Up to second derivative. Now, third derivative need not be smooth. So under that interpretation, polynomial is smoother. Okay. And if it is just that which of them is smooth, then both of them are smooth. And that was the answer in the answer key. But then this ER is not explained. So I don't know. But did you understand the subtlety here? It's all in semantics, how you interpret. Okay?
I had one question.
Yeah,
By the definition of spline interpolation,
yeah.
uh, actually I'm not. So spline is you're telling that it could be a second order. It can only do. So could you
Up to
give me an
second,
example?
yeah, let me do it. For example, let's restrict ourselves to cubic spline. Okay. In cubic spline, we know that second derivative is smooth, is continuous. Okay, so let's take an example. This is a polynomial. Okay, and whatever the slope is here, I'm continuing in the same direction another polynomial which is like this. Now is it or can it be a cubic spline? Okay, so you got my question. This is one uh, quadratic polynomial and this is another one, and it is guaranteed that both these slopes are same here at the patching point or merging point. So it looks very smooth. If you zoom in, you see that it's a straight line because both the slopes are equal. But could it be a cubic spline? No, because the condition is that the second derivative is continuous. So this is a quadratic which has this downwards curvature, right? So its curvature or second derivative is going to be negative, right? Let's say it is minus x square, then its first derivative would be minus 2x and the second will be minus 2, right? And these other terms don't matter, right? If we have plus bx plus c, this derivative will be minus 2x plus b. This c will get killed, and for the second derivative, b will also get killed. So it's the signature of x square that matters. So if this is some minus 6x square plus 3x plus 2, and this is 5x square plus 2x plus 3, and it's in such a way that here both the values and the derivatives are equal. But still it won't be cubic spline, even though it looks very smooth, because the second derivative here it's plus 10 and here it's going to be minus 12. Okay, so that is not continuous. So what we mean is that curvature should be continuous. So if it is going downwards, it has to start by going downwards and then it can go upwards. Okay, this is something you cannot see using naked eye, but this is the concept. So it may look smooth, but it need not be a spline, cubic spline. Okay, now does that answer your question?
Yes, yes, it
Sorry, you want me to
yes, it
explain
answers
again?
my question.
Okay, yeah,
No, 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 no.
yeah. Okay, where would yeah. Okay, and there is another interpretation also. I think that is the worst interpretation, and that is that in Lagrangian you get a lot of spikes and oscillations, right? And you might argue that to someone who just know the English definition of word smooth, they might say this is not very smooth because it's oscillating and everything. And under that interpretation, spline would be smoother. But I don't know. I would say either one or three. It's up to you. Hopefully, these kind of questions will not be asked in exam. But okay, okay, let's go ahead. If you have any questions, just unmute yourself and ask. Okay. Now there are some easy questions. What is the degree of polynomial of n data point in Lagrange interpolation? Answers in the chat box. One, one. This is n minus one. Yeah, so yeah, everyone is getting it. Right, this is something that we know because Li is going to be n minus 1 degree polynomial, and you know that if you have n points, let's say 3 points, then you can pass a parabola. If you have 2 points, then you pass a straight line, which is just degree 1. This is degree 2 for 3 data points. Okay, so degree is always 1 less than number of data points. Okay, what is the error formula for Lagrangian interpolation of function with n data points, where x is the intermediate, sorry, zeta is the intermediate point? Again, one, Anil Kumar, yes. Okay, so let's look at again here they have given the definitions, the distance between the data points. So one has this n minus 2 and n square and nothing. So we know none of them can be correct, right? Because it's up to nth differential. And then the product is x minus xi. This is given in the lecture notes. Okay. And what I wanted to point out is that this is eerily similar to Taylor's formula, right? Taylor series. In that you get fn of x, or rather x0, from which you are doing the series expansion, and then you have x minus x0 to the power n. This is the nth term in the Taylor expansion of x, right? So just the nth term is going to be this one. And now you can draw some similarities. X0 is substituted by zeta. So it is not going to be exactly at x0 because to begin with we don't have one x0 from which we are expanding. We are kind of expanding from all xi's. Okay. So we are not just expanding from here what is happening. We are taking into account what is happening here, then here, then here. So it is like expanding from all the points and then combining. So this x minus x0 to the power n, which has n terms in product, is still n terms in product, but it is x minus xi. So x minus x0, x minus x1, etc. Okay. And then zeta is going to be somewhere in between x, all these x's. That is the intuition. Okay, it's not a proof, obviously, but you can use this to remember this formula, if nothing else. All right. Okay, now some time for some labor work. So Lagrange polynomial is given, and if some of you may have already done this on Sunday, if not, then uh, wear your calculative helmet and let's start. So what is given is that at 15 the value is 24. Okay, and at 18 the value is 37, and at 22 value is 25. This is not some standard notation. Okay, I just invented. You can invent your own notation. So these are x values, and in bracket are the y values. Okay. And then it is already given that the f2 of x, which is p2 of x, is L0 of x times 24. So this is y0, right? This 24. Then L1 of x, y1, and L2 of x, y2. And they are just asking us to evaluate L1 of x at 60, at x is equal to 60. So we know the formula. It is x minus something and x1 minus something because we have 1 here. Okay. And this you do for all the points. So how many points do we have? 3 points, right? So you do this for 2 points because 1 has to be excluded. So now you in the first one you put x0, in the second one not x1 but x2 because we are dealing with 1. Okay. So this is how I like to write it. You can have your own way of remembering. And if you are not writing the exam, by the way, don't bother remembering all of this. It's just trash. But if you are writing the exam, there is a chance that these kind of questions can be asked. Okay. So now x is 16. What is x0? 15. x1, 18 minus x0, 15. And then again x is 16 minus x2, which is 22, and x1 minus x2, which is 18 minus 22. So this is 1 over 3, and this is minus 6 over minus 4. Okay, so this becomes plus 3 2s are 6, so 2 over 4 or 1 by 2, which is zero point 0.5. Okay, maybe some of you answered it. Zero point 0.5, yes, Anil Kumar. Nice. Okay, so we got one of the Li. In the same way, you can calculate L2 of 16 also, right? And L0 of 16. And once you have all those three numbers, you can calculate estimated value at 16, which should be close to 24, by the way, because it's close to 15. But then there could be oscillations also, so you don't know. But I think most likely, since we have just 3 points, you can check it yourself. It will be close to 24. Okay. Any
One
questions?
query.
Yeah.
So, just a little basis, like if you see this formula for L1 of X, it looks
Mhm.
as if it is Product of two slopes.
Two slopes. Okay. Well,
Does it make sense if I tell?
if it makes sense to you, then sure. But I mean, it doesn't look slope to me because we don't have y here,
Okay,
right? It's not delta y or delta x.
right, right, correct.
One way you can think is x minus x0. So our x is somewhere here, right? This is 16. So x minus x0 is this distance and divide by this distance. So this gives one fraction. It's the fraction over this first length where the x is. And the second one is x minus x2 upon x1 minus x2. So x minus x2 is this one upon x1 minus x2, which is this one. So that is a fraction starting from x2 where it is on this line. Okay. So now we know that x is not here, but it's in this direction. So this is 0 fraction, this is fraction 1, and this is fraction like 1.5 or something. So in fact, it is 1.5 if you look at it. So this is one way in which you can interpret this. Okay,
Right, thanks.
yeah. Okay, eighth one in cubic spline interpolation, the first derivatives of the splines are continuous at the interior data points. Second derivatives of the spline are continuous at interior data points. Derivatives of the splines are continuous at the interior data points. And the third derivative, which one is correct? Let's see what Janta says. 3, okay, 2, alright. So, first of all, it is mentioned in the class note that second derivative is continuous, right? This is undisputable. Now, what it means for these three options, let's say. First derivative is continuous. Now, if second derivative is continuous, which means that first derivative is continuous, right? Because first derivative is the integration of this function, and any integral of a continuous function is going to be continuous. So this is correct. Second derivatives are continuous. This is, yeah, it's given in the lecture. Okay. Derivatives of the splines are continuous at interior data points. Now, this it depends on what we mean by derivatives. Okay. But it's given that it's a cubic spline and it is at interior data points. Okay. So does it mean some derivatives or all derivatives? I I would like to interpret it as all derivatives, but it's unclear. If it is all derivatives, then it need not be correct, right? Because let's look at this one. The third derivative can be discontinuous. Okay, it's just up to second derivative. So if we interpret this as all derivatives, then I think 1 and 2 are the correct ones.
So if we have such a kind of question that we can select the two options,
Hmm.
like it is not MSQ, like it is not MCQ, MSQ is in there.
In the exam,
Yes, sir, and
uh,
here also.
here
In
I
the
think
assignment
no.
also.
In the assignments, is it given? I'm not very sure.
No, such a kind of question we have in assignment. If any of them like having the two option correct one,
Mm-hmm.
then we don't have that option that we can select the two of them. So how we can recognize whether the two correct or one correct?
No, it must be mentioned in the instructions. Is it not the case?
Like last time when we have such a situation, then they said that there is a square box for selection. So
Ah,
it means
yeah,
that miscue, and it is a round isn't there, then it is a
true.
like
So
MCQ. So it is same for this one also, or like
I
in this
don't know
question also.
for particular this one, but yeah, in general you have radio button for single one and checkbox for the multiple ones, right?
Yeah, but here
So,
also the question you have wrote that having the round option, and
hmm,
then we select the two options are correct one. So
yeah,
that is the concern because it is not like mentioned in the question that it is
hmm,
a MCQ. So first two options are correct, and there is a no things regarding that.
true.
So I
So,
choose the third one.
okay, I see. Is it there in this year's assignment? No,
No,
right?
that no, like fourth question is like similar to that, but it's related to the polynomial, and it is
Okay,
related to the this one. This
true.
is also here not continuous everywhere, and then no, we have that
Yeah. So
correct
in
things.
this only one is correct, right?
Yeah, yeah.
Yeah,
But
then.
if we have like that one now in your question also, you said
Mhm.
that two options are correct one,
Hmm.
but there is a round over there.
Yeah, yeah. So it means whoever designed the questions either messed up or they didn't know that it's going to be a single correct question format in the assignment.
So
Okay,
in exam also we have the MSQ or only MCQ is in there.
okay. That I'll have to ask and let you know because I'm not part of NPTEL as such, so I'll have to ask and I'll let you know next time. Okay.
Yeah.
But in this one, just for the sake of truth, all of us agree, right? The first two are correct and next two are not. Okay. Now one Bahubali question. Find f of 3 using Lagrange, and what is given is you have 0. At 0 the value is 2, then at 1 value is 3, at 2 value is 12, and at 5 the value is 147. Okay, and what we want to find is at 3. So this is our x. Okay, so what's the formula? F of 3 is sum over Li of 3 y I, right? Where I is from 0 to 3. So we want to find, so with this y0 are given, right? Y0, y1, etc. So we want to find Li of 3. So first L0 of 3, then L1 of 3, etc. So L1, L0 of 3 is going to be 3 minus, right? X minus, and then here it's going to be x0, which is just 0 minus. Okay, and it's going to be the same thing. How many terms will be there? 3, right? Because in total you have 4 terms. And 3 minus and 0 minus. And now you put x1, x1, x2, x2, x3, x3. So, did I make some mistake? So this should be x0 minus x1. So you start from 1. Yeah. So x1 is 1. So it is going to be 1 and then 2, 2, and 5, 5. Is this correct? Yeah, I think so. So it is 2 times 1 times minus 2 divided by -1 times -2 times -5. Okay, yeah. So we total have 4 negatives, so the answer will be positive, and this 2 will get cancelled. So we have 2 by 5. Okay, the same way L0 of L1 of 3. So on the top we have distances from 3, right? But we ignore 1 because we are calculating 1. So it is going to be 3 minus 0, which is 3, then 3 minus 2, which is 1, and then 3 minus 3 minus 5, which is going to be minus 2. Okay, and then you calculate the difference between this and these 3 data points, right? Because we are calculating L. So it is going to be 1 minus 0, which is 1, then 1 minus 2, which is minus 1, and 1 minus 5, which is minus 4. So now we have 3 negatives, so the answer will be negative, and it will be 3, 3 by 2, right? Yeah, okay. So, and then should I do it or just write the answer? Maybe I can do this. For the next one, I'll just write the answer. Okay, L2 of 3. So now we are ignoring the second one. So I write 3 minus 0, which is 3, then 3 minus 1, 3 minus 1, which is going to be 2, and 3 minus 5, which is minus 2. Upon now we calculate distances from this 2 because we have 2. So 2 minus 0, which is 2, then 2 minus 1, which is 1, and 2 minus 5, which is minus 3. So this will be plus 2, right? Yeah. And L4 of 3, again 3 minus 0, 3 minus 1, and 3 minus 2 upon calculate from 5. So 5, 4, and 3, right? So this 3 will get cancelled. So 1 by 10, right? So now our answer f of 3 will be, or how do we write, P4 of 3 is sum over Li times Yi. So plus 2 by 5 times the value of Y0, which is 2, 2. Then minus 3 by 2 times value of Y1 plus 2 times Y2 and plus 1 over 10 Y3. And those values are 312 and 147. 312 and 147. Now I won't do this one, but it will turn out to be 35. Okay, so this is the answer, f of 3 or p4 of 3, whatever you want to call it. It will be 35. Yeah, correct. And as you can see, it's not there in the options. So maybe they did some mistake, or they intended to write this as 3 or 4. There is some either typing error or calculation error, but the answer should be E, 35. Right. But I hope you get the idea. In case you encounter such crazy looking question in exam, you just have to, grind it. Start from L0, calculate from 3 the distances on X, and then calculate the distances from 0. Then go to 1, do the same thing, ignore 1, and then calculate distances from 1. Then go to 2, ignore 2, and then calculate distance from 2, etc. Okay. So if you do some 5 or 10 such questions, you will get the idea. Okay, the last question.
One query.
Yeah.
In this question,
Hmm.
sorry, I'm asking a basic question. What is the physical significance of Lagrange formula?
What is the physical significance? So, what we are saying is that if we have what we mean by linear average, let's say we are trying to calculate average age, okay, and we have two kinds of people in the classroom. This is male and female, and average age of males is this much, and for females it is this much. Then let's say this is y0, this is y1. Then what is the average age? Yeah, you might say it is y0 plus y1 divided by 2. But this need not be correct, right? Why? Because you don't know how many males are there, how many females are there. So you have to do a weighted average. So you said that n male, which is the number of males, divided by total number of people, y times y0 or y male, and similarly for females. Okay. So what we are saying is essentially that this average y is some combination of y0 and y1, and there are this coefficient which is just a fraction of male and female. In fact, you can have right now we all know that there are multiple genders, so there is another gender LG, right? So you can write plus y2 plus y3, and there are going to be some coefficients here. So the physical interpretation of this Lagrange is this same thing. It's the weight by which yi is considered. Okay. So if L1 of 3, let's say, is close to 0, what it means is that where 3 is doesn't matter. What's the value of 3? Okay. Sorry, 1, because L1 is 0. So you can change this point and it's not going to matter so much. On the other hand, if you have L2 of 3, which is very large, then what it means is that this point is given higher weightage than 1, much higher weightage. Okay. So this L's Lagrangian multipliers can be thought of as weights by which these yi's are given importance. Okay, that's how I see it.
Okay, thanks.
Okay, yeah, right. Because at the end, what we did something times 2, which was the value of 2 y0, then something times 3, something times 12, and something times 147. And all of these have different weight. And you see which one has the highest weight? This one, 12 wala, right? And 12 one is 2. Why does it have the highest weight? Because it is closest to 3. Okay, and that makes sense. If you are going to be close to here, influence of this point is going to be the maximum, right? So that's the idea.
Right.
Okay, last one, and I promise I won't do this because it will take another 15 minutes at least. But again, we are given some data 4, 6, 8, 10. There is one surprise here. We have 1, 3, 8, and 16, right? And find the polynomial for the data. So, a very straightforward looking question. But one subtle thing is that since we have 4 data points, superficially we should have cubic, right? Cubic polynomial is 4 minus 1, which is the degree. So 3-degree polynomial, which is a cubic. So answer should be cubic polynomial. And in fact, I had seen such question with just one option that is cubic. I would have ticked that one, and I would be so wrong because you see there are no cubic polynomials. And what's the reason? Well, the reason is that coefficient of x cube could be 0, right? One has to design data points such that this happens, because if you do it just randomly, it's not going to be 0. But in special cases such as this one, it could happen, right? And now we are not given any x, we have to find the polynomial. So again, the drill is find L0 of x, which is going to be, I'll just do L0. So x minus, ignore the 0. So 6, then x minus 8, and x minus 10, and then calculate the same distance from the same points from 0. Okay, so this is 4. So 4 minus 6, 4 minus 8, and 4 minus 10. So it will be x minus 6, x minus 8, x minus 10. On downstairs you have 2 times 4 times 6. 6 fours are 24 and 48 with a negative sign. So this is minus 1 over 48, x minus 6, x minus 8, and x minus 10. Okay. And one thing that you should remember in such question is that we have something like this, right? X minus beta, x minus gamma. So this is going to be a cubic, right? So something x cube, and the coefficient of x cube will be 1, right? Because you will be multiplying these three terms. That is the only combination that will give you x cube. Now for x square, you have to multiply two x's and one of this, right? So it could be x square times minus gamma, or you can multiply this two and use this one as the constant. So it would be minus beta. So all in all, x square will have minus alpha plus beta plus gamma. And we know this alpha, beta, gamma are just the roots, right? So alpha plus beta plus gamma is the coefficient of x square. So minus of that should be the sum of the roots. And then the next one is the pairwise product, right? Because you are using just x, so you have to use alpha into gamma, then beta into gamma, and alpha plus gamma, gamma alpha x, and last one will be just alpha beta gamma with negative sign, right? So if you remember this, you can expand this. Maybe I can just write out minus 1 over 48 x cube minus 24 x square plus 188x minus 480. Okay. Similarly, you get L1 of x as something, L2 of x. Okay. It's painful, but definitely doable, right? And in fact, you have a programmable calculator, and if it is allowed, then you can use it. And then just sum over all x with y0. Okay. L1 of x, y1, L2 of x, y2 plus L3 of x, y3, and the final answer would be 3 by 8 minus 22 by 8 and 6 x square x and plus. Okay. And why? Because this x cube coefficient magically becomes 0 when you do this addition. You will see that y0, y1, y2, and y3 are such that they are set in such a way that this becomes 0. Okay, so this is the answer. Again, unfortunately, it's not in the solution, right? So if this was just 48, then this becomes the correct answer. Okay. Okay. Any questions?
What is the last answer, sir?
Uh, Last answer is this one. Let me just write it. 3x square minus 22x plus 48 divided by 8. Okay, that's what I got, and I think it is correct because in Agrim's code you can enter. I think he has already done that, and it gives out this answer. Okay, so let me just erase this. Can create the confusion. This one. Okay.
Yeah.
Yeah. Okay. Any questions about anything?
I mean, in the final exam, those are MCQs, right? MCQs and five coding problems.
That's what I am told. Yeah, but I'll reconfirm if they are MCQs or MSQs. Multiple select questions or just multiple choice question.
Okay.
Okay. I'll confirm.
Okay.
Okay. Okay. Any other questions? If not, then
One gen,
yeah.
uh, I was talking about the experimental data.
Mm-hmm.
If we have, say, from a 5 volt probe, you have got many velocities,
Yeah.
ux, uy, uz,
Mm-hmm.
and suppose I take an RMS or I use uy, say,
Mm-hmm.
and then using that SymPy,
Mm-hmm.
I can get the polynomial,
You can get the polynomial, Lagrange polynomial.
right?
Yeah.
So, but it will so happen that the polynomial will not pass through all the experimental data points, right?
No, that can't happen because the way Lagrange polynomial is constructed, we saw that it will pass through all the data points,
Okay, okay, I understand.
right? You can look at it again, but we saw that error becomes zero at that point. And even
Right,
otherwise,
right.
if you just plug in the value of any given data points in the formula for Lagrangian polynomial, you get the same data point as answer. Okay.
Okay, okay. Thank you.
There is one question by Anil Kumar. Is there any functions SL prep in scipy.interpolate module to find spline interpolation? Uh, I don't know if I think you are asking for in general. I know this one. This is Agrim's, which uses the kind. So this function. So I think this kind variable can take. It's a parameter can take different values. So all the known or popular one, all those popular splines should be here. Is it what you are asking?
So am I audible?
Yes,
Okay, I think that function is for interpolation, linear
yes,
interpolation, I think.
yeah.
But I'm asking for spline.
No, no, this is not linear interpolation. This is a cubic
That
spline
I'm
interpolation.
talking about that interp L1D, that
Yeah,
function.
yeah, yeah.
That function is for linear interpolation,
True,
I think.
right.
Okay, but in the recent assignment,
Hmm.
uh, they are asked for what is the function for this spline interpolation in scipy.interpolate. But I think options they are misspelled it. I think the function is
Function is Your voice broke
Maybe he is asking about the question number 2 in assignment 4.
in assignment. Okay. In
Assignment
the
4,
in the
question
current
number,
current one.
yeah, current. This one, question number 2. Yeah.
Question number two. What is the linear? Yeah, so it was this one, right? Oh, actually, I should not be saying anything because,
Yes.
yeah, yeah,
That's why he asked the question maybe.
yeah. So I'm sorry, I cannot discuss this question right now because it is still open, right? Due date is tomorrow. So maybe next time we can answer. Right now, whatever you think it is correct, just
So I am not
take it.
asking about the question. I think
Mhm.
there is some error in that options.
Yeah, but is it obvious or is it confusing?
I think it is a typing error. None of the
Yeah.
option is correct, as far
Okay.
as that
But
option is concerned. None of them are correct.
yeah, is there any option which is very close to the
Yes,
correct
yes, there
answer?
is an option. There is an
Yeah.
option very close.
Then just tick it.
Okay.
Yeah. Okay. Anything else? Sure. Then let's meet next week. Okay. Same time, same link. Bye bye. Thank you.